If you recall, yesterday we talked about parameterized curves. This is where we describe coordinates as a function of some parameter. The main motivation for this, at least for now, is that we want to be able to describe a one-dimensional curve in three-dimensional space. We want to describe a one-dimensional curve in three-dimensional space. We can't use a function or an equation because a function or an equation in three variables is going to produce a surface. So if we use an equation or a function in three variables, we end up with a two-dimensional surface in R3. So we're going to use parameterized curves because we want to describe a one-dimensional curve in R3. Yesterday we described a circle. Actually, we described a helix because we put a z-axis on. I just made the z-axis go from 0 to 2 pi. So we need to learn some basic shapes. So today we want to parameterize a line. So we want to talk about the parametric equations. So we want to parameterize a line today. To find the equation of a line, we just need 2 points, and that's what we're going to start with here. Question? So a function might be y equals the square root of 9 minus x squared, where the equation would be something like x squared plus y squared equals 9. Or a function of two variables where you solve for one variable, c equals, and then something with that x and y. The equation would be like x squared plus y squared plus z squared equals 9. That would be a sphere with a radius of 9. That's an equation in x, y, and z. We don't write one variable as a function of the other variable, one variable in terms of the other variables. So the function, one of them will definitely have a z to the first power. So let's write the parametric equations of a line. All we need is 2 points. And we're just going to use an example. Find parametric equations of the line containing -2, 1, and 3, and 5, 5. Let's not use the same stuff. In R2 or in R3, 2 points will determine one line. So here we have 2 points in R3, and we want to make a line containing those points. To describe a line, we need a place to start. That's one of these 2 points, and a direction to go. Classically, in R2, we've described the direction with slope, a rise and a run, a change in y, and a change in x. So we need 2 things to describe a line: place to start, direction to go. Need spelled D wrong. We need a place to start and a direction to go. Normally, the direction to go would be the slope, which is the rise over the run. Because there's only two of them, we just make a ratio out of it. The change in y divided by the change in x. So the direction to go contains two things, the change in y and the change in x. But now we've got three variables. We've got x, y, and z. So our direction to go is going to have three parts. I need a change in y, a change in x, and a change in z. We need a change in x, a change in y, and a change in z. That's how we're going to and then we're going to take those three deltas, put them into one vector, and that will be our direction vector. So notice that this direction vector goes from the point -2, 1, 3 to the point 5, 7, -1. So our direction vector would be 7, 6, -4. This will take us from the point -2, 1, 3 to the point 5, 7, -1. Notice that this has a direction. This one started off at -2, 1, 3 and ended at 5, 7, -1. As long as we're consistent, it doesn't matter what we use for the vector. If I had switched these around, I might have said that delta x was -2 - 5 or -7, and then delta y would be 1 - 7 or -6, and delta z will be 3 minus a -1, 4. So this is just going to produce the opposite vector from 5, 7, -1 to the point -2, 1, 3. Both of those vectors are lying on the same line. They're just pointed in different directions. That's just a matter of perspective. So what we want to do is describe the equation of a line the same way we always do. Write down where you start, and then write down your direction to go and multiply by how many times you want to do that. We're still going to do y equals b plus mx. So we're going to still think about y. We're still going to think about y equals b plus mx, where b is the place to start and m is the direction to go. And when we can write y as a function of x, then x is serving as the parameter. So we start at b, go in the m direction, and x is the number of times that we do that. We're going to do the same thing with this problem. Our equation is going to, we're going to write down our starting point. I'm going to start at the vector -2, 1, 3. And I'm going to add the direction vector and we're going to do this a bunch of times. I'm just going to multiply that by our parameter t. Note that I changed referring to my starting point as a starting point in parentheses, an ordered triple, and I traded it in with a vector. This is so I can add it to my direction vector. There's our equation of a line. I wrote it as a vector equation. Let's say P of t. When t is equal to 0, we will be at the point -2, 1, 3. So we'll be down here when t is equal to 0. And when t is equal to 1, I will add 7, 6, and -4, and end up at 5, 7, -1. So here's where we will end up at t equals 1. If we just multiply this out into one vector, we'll see the 3 parametric equations for our line. The x-coordinate will be -2 plus 7t. The y-coordinate will be 1 plus 6t. And the z-coordinate will be 3 minus 4t. Here are our parametric equations. So P of t, that could be our vector equation, and I could break that into 3 parametric equations. These aren't the only parametric equations that we could use to describe this line. There's one other obvious choice, and that would be using the vector w, starting off at 5, 7, -1, and just going the opposite direction. So in some alternate reality, there's some version of Professor Leach that's doing this backwards. 5 minus 7t, y of t is going to be 7 minus 6t, and z of t will be -1 plus 4t. But we're describing the same line. We're going in the opposite direction. Instead of t equals 0 being -1, 3, t equals 0 will be at 5, 7, -1, and t equals 1 will be at -2, 1, 3. Any questions? So good news. There's more than one way to write the parametric equations of this line. Bad news. There's more than one way to write the parametric equations of this line. hard mode of time. Oh, enjoying your conference class? Listen to the sounds of people having fun. And then I get to, in the middle of the class, go walk over and close the door. It's like, well, let me shut you off from that fun. I know. I get to have fun. Them's the rule. Extra fun. I get to be mean and I get to do that. So it's like double mean. So we actually have a lot of control over this. We could say this is going too fast, going from -2, 1, 3 up to 5, 7, -1. It's too fast to do that in t = 0 to t = 1. So we can slow this down by changing our delta t. So this part right here, 5 minus 7t. 5 is where x starts. -7 is the delta x over delta t. So this -7 is how x is changing with respect to t. This -6 is how y is changing with respect to t. And this +4 is how z is changing with respect to t. So here we go from one point to the other. I should have named them P and Q. We go from P to Q in 1 unit, or from Q back to P in 1 unit on our parameter. But as long as we change the delta t all the way across, I can't remember like 6 whole numbers after turning the page. See? I wrote it down so I wouldn't have to remember. If the x goes in one direction, if the x goes the opposite direction, then t goes in the opposite direction as well. So fine. So this goes from P to Q in as t goes from 0 to 1. But we might look at this and say, this is too fast, let's slow down. Let's go from P to Q in 10 units. So I want this to go from t = 0 to t = 10. So instead of my delta t being 1, I'm just going to change my delta t to 10. My delta x, delta y, and delta z can all remain the same. Just slow down your delta t. Now when t is equal to 10, we add 7 to the x, 6 to the y, and subtract 4 from the z. Just change the run all the way across, and it won't change the angle of the line. Won't change the direction of the line. So we can see that we have lots of control in describing the line. We can control how fast it's going. We can control which direction it's going, from left to right or from right to left. We can even move things around depending on where you're at with your manipulation of functions. Maybe I don't want 0 to 10 to be the 10 units that it takes. I want to go from -3 to 7 because reasons. So if we change to the interval from -3 to 7, we get to start -2 when t is equal to -3. From t equals -3 to 7. It's still a 10-unit interval from -3 to 7, but it's not from 0 to 10. It's from -3 to 7. So we have a lot of control about how we describe the function, how fast we're going to go from point P to point Q, which direction we're going to go from P to Q or from Q to P, as long as we're consistent in our delta X over delta T, delta Y over delta T, and delta Z over delta T. Breaking it up into parametric equations allows us to have 3 different slopes, 3 different relative rates of change. X with respect to T, Y with respect to T, and Z with respect to T. And the X, Y, and Z all get to be independent of each other. Any questions? How's everybody okay? I was do this last one because I'm not sure how comfortable people are with like horizontal and vertical shifts and things like that. Calc 1 is too late. This comes up in trig. Trig is the first place you really start seeing horizontal vertical shift, horizontal vertical stretch. Kind of the first place you really start to look at that because you get those functions. The sinusoidal functions are really good for this because they always look the same. So you can see that horizontal stretch and shift, the vertical stretch and shift, and the horizontal stretch and shift. Because you can see the period squish or stretch, and you can see things move back and forth. If you were raised to say phase shift, I was also raised to say phase shift, but then someone said there's only one function there, say horizontal shift. Because phase like needs to have 2 things. I don't know. Then I was told to stop saying phase shift, so I stopped saying phase shift. I was still a student. I was doing what I was told. Plus, changing the period is a horizontal stretch or compression, and we don't call it a phase stretch or compression. So don't try to sound fancy by saying phase. Just say horizontal. That's a better description anyway from a math standpoint. You know what I mean? Is everybody okay? Every time I think about this, I'm in a Calc 3 class and I don't know my Calc 3 students. for the most part, in the spring semester, my count 3 students were not my count 2 students or my count 1 students. So it's like a whole new class for me, like a new batch of students. I don't know if I should call you a batch of students. Is that insulting? Crop of students? I don't know what do you call a group of students? Okay, batch of students, like a batch of cookies. So, herd of students, a gaggle of students. A horde of students. See, these words start to be more descriptive of what the students might actually be doing. It's like this is a batch of students. It kind of sounds like that's for like when you first get here. Like in the first couple of weeks, this will be a fresh batch of students. This batch goes with fresh, right? So like a horde of students would be like, it'd have to be a lot of yous, and you'd have to be doing something that would be like that would be horde-like. So if like all the students at Skyline got up and walked out in protest, there would be a horde of students protesting. And it would be weird to say a batch of students protesting. So I think this whole different names for groups of different animals is weird. Anyway. Now I'm thinking about that. But the problem is, I don't know what you were shown in your trig class. So I have to bring this up. Let's suppose I write a sinusoidal equation. Y equals A times the sine. It could be cosine. I'm going to use cosine because I like cosine better. A times the cosine of B times X minus C plus D. What does A being multiplied by the cosine, what does A do to the graph of cosine? Anybody remember what A does? So A is the amplitude. That's the distance from the middle to the top, right? So we got this sinusoidal graph. Because it starts at the top. There's top, middle going down, bottom, middle going up. Those are the 4 different points that I refer to. So the next number is B. B is being multiplied. And it's not actually the period. The period is 2 pi divided by B. So that's how we figure out what the period is. C is our horizontal shift. I usually refer to this as the start, and I always put it in quotes because it goes on forever in both directions. And then D is your vertical shift, the middle. So there's like a middle here. Your amplitude is the distance from the middle to the top and from the middle to the bottom. And the distance between any 2 corresponding points is 1 period. Remember making sinusoidal graphs? Think about the order of operations on what's going on with X. Think about if we start with an X, what's the first thing that happens to the X in the order of operations? First thing is we subtract C. After we subtract C, what do we do to the result? Multiply by B. So operation number 2 is we multiply by B. Then what happens after we multiply by B? We apply the cosine. After we apply the cosine, what comes next? Multiply by A. And finally, add D. And we end up at Y. This is the order of operations that turns X into Y. This is what we want to notice. Notice in the middle, we've got this cosine, and we had two operations before the trig function and two operations after the trig function. So here is in the middle where we're at the trig function. This divides into two regions, before and after. Before the trig function happens, we have subtracting C. What is that? What effect does that have? Subtracting C is the horizontal shift. Multiplying by B is going to produce horizontal stretching or compression. Then the trig function happens. And we've got another multiplication and another addition. Multiplication by A produces a vertical stretch. And adding D produces a vertical shift. Things that happen before the trig function are horizontal things. Things that happen after the trig function are vertical things. And we take that thing in the middle, the trig function in the middle, as our base case. And we modify it with horizontal stuff by doing stuff to the variable before the function happens, and vertical stuff by doing stuff to the function after the function happens. The same thing happens if we make a parabola, for example. We just usually don't combine, don't separate out a horizontal shift and a vertical shift in a parabola. We just have one vertical shift outside. Horizontal stuff happens before, vertical changes happen after in the order of operation. Addition and subtraction produces a shift. Multiplication, division produces a stretch. It's important to recognize these kinds of changes so that we can adapt this kind of thinking to more complicated versions. What if I throw in an x squared? If I have the cosine of x squared, I'm altering things horizontally. I'm making infinity show up faster, and so we're going to compress the graph of cosine more the further down the x-axis we go. If I square the cosine after the cosine happens, so cosine squared x, I'm squaring vertically. And I'm going to take the bottom of cosine, I'm going to flip it up positive, because even exponents don't respect negatives and they make everything positive. They're like, oh, I'm an even exponent. Why don't you just cheer up? You're like, oh, listen, motherfucker, that's not how sadness and depression works. Stuff it. I don't like even exponents. It makes solving more complicated. But the square has the same effect. It's just making infinity show up faster. The negatives become positives. So we know that if we have cosine of x squared, then instead of just, it's going to get crammed up. The oscillations happen faster and faster and faster because we're moving infinity closer. We're moving along the x-axis faster. But if we cosine squared x, then everything's going to be positive, but we're not going to have any kind of horizontal changes. The same kind of thinking can be applied to the 1 over x function. 1 over x takes 0 and sticks it at infinity, and takes infinity and sticks it at 0. It flips the x-axis around. So that's why when you look at the graph of, say, cosine of 1 over x, when you look at the graph of cosine of 1 over x, we're trying to get an infinite number of oscillations before we get to 0. So starting here and then at 0 at the door, I got to put an infinite number of oscillations. That's why the graph looks so jacked up for cosine of 1 over x. Horizontal changes and vertical changes. Anyway. Horizontal changes, shifting things back and forth. That's it for today. I will see you all on tomorrow. Everybody have a good day. Parameterize some lines, and thanks for playing. And grab a cookie on the way. See you tomorrow.